But our next order of business is to follow a progression that is very similar to Physics 1. So we're going to go from forces to energy. So if you remember, this is the same progression that we did in Physics 1, where we used F net equals ma. And to find the net force, we sum up all the forces. And vector addition is a pain, right? This whole idea that you have to do break everything into components, do the SOHCAHTOA, blah, 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 this kind of stuff you're dealing with in homework 1, right? Whether it be with forces or the proxy for forces, which is field. In energy picture, this was our master energy equation from Physics 1. We, of course, had non-conservative work like friction. But if we don't have that, then the E, which stands for mechanical energy, is just potential energy plus kinetic energy, right? And that was far easier to do, right? It's probably one of your favorite methods from Physics 1. It's because if over here you're doing vector addition, which is annoying, over here you're doing what's called scalar addition. You're just adding up numbers. Adding up numbers, since you've done since kindergarten, it's a lot easier to add up numbers, right? Let me remind you of some advantages of energy. The acceleration does not have to be constant, right? You can do all sorts of crazy stuff like roller coaster loop-de-loops and stuff. The one thing we do give up, however, is what? What's the one thing that you lose the ability to compute? Time. So, as we do the same thing in our situation, we move towards energy. We're going to lose the ability to compute time, but our trajectories can be quite more complicated. Now that's really important for us, okay? Because if you have a uniform field, then a uniform field means that it's, of course, constant in size and direction, which means that the force if the electric field is constant, what does that mean about the force? Constant. And that, of course, you can tie into F net equals ma. What does that mean about the acceleration? Constant. And then, you're in business, you can use a whole set of equations called the constant acceleration equations. Remember from Physics 1, right? There were the 5 equations. Maybe you know them as the kinematics equations. I mean, that was basically your first 5, 6 homeworks in Physics 1, right? This idea is that you find the net force, you find the acceleration, then you can put into your constant acceleration equations and find whatever you want. But we couldn't do problems like this in the force method, right? Forget that. We had to go to energy for that. Here's the problem. This only works if you have this. And this is definitely not usually the case, right? So if you have a non-uniform field, which is most things, then you will have a non-constant force, non-constant acceleration, and you can't use that stuff. So it's very blindingly obvious here why we have to go to energy. And you'll note there's a conspicuous absence on your homework 1 of ever letting a charge move and asking about it evolving its motion. The reason why is because if a charge is actually moving through a field that is not constant, then we can't use these equations. We have to go to energy. So that's the next order of business. We're going to look at charges actually moving from place to place, generally doing it through a non-uniform field, and we have to use energy, just like we have to use energy on these roller coaster loop-de-loops. Okay? So we're going to go to energy method. So in general, we look at a charge trajectory through a potentially non-uniform field, and we're going to want to go to the energy method. Because the acceleration is not constant, we can't use those equations at all. Now the one thing we of course give up is time, so I won't ask you for the time. The electric field hockey lab, it actually does show it to you with time. That's of course is a computer. And a computer can do the much more complicated calculations it takes that are far beyond the scope of the course to figure out how these things would proceed even though the fields aren't uniform. So let me give you a little preview of what we're going to do. So if this is the force picture and this is the energy picture, I guess let me put it like this, force and energy. We have a direct way of contacting between them. Here, of course, we talk about the mutual force of attraction and repulsion between two charges. And here we'll talk about the potential energy that's stored when we bring two charges together. Obviously, if you say you bring two plus charges together and you let them go, they fly apart. They gain kinetic energy, it had to come from somewhere. Where? Potential energy. And then we have the separate, the middleman approach, where they don't get to have a direct conversation, they do it through a proxy. The middleman for force is called the electric field. So one charge makes one and the other one feels it. We're also going to have a proxy for energy. One thing makes it, the other one feels it. This is called voltage. Okay? So one charge makes voltage and the other one sits in that voltage, and that's the proxy for calculating energy. So we'll get into the details of that next time. That's it for today.